Well, we come now to a program for the second level Introductory Electronics course. It's concerned with the measurement and underlying theory behind the frequency response of an electronic system.
This program is about sine waves, and to start I'd like to show you something about them that you can't do very easily with your home kit, and that's the addition of two sine waves of the same frequency. Well, that's one of the sine waves displayed here on the oscilloscope. It's generated from a signal generator, and there's the oscilloscope trace alongside it. It's 8 volts peak to peak, or 4 volts amplitude. Here's another sine wave of the same frequency. I'll switch it on. This one is 6 volt peak to peak, or 3 volts amplitude. As I turn the knob, the phase of the 3 volt sine wave can be varied with respect to the 4 volt one to give us either a lead or a lag. It can be varied to give us 90 degrees lag in that position. Now, what I want to do is add the two sine waves, and that's what this box does. First of all, let's try it with no phase shift. Well, there's the summed waveform, another sine wave just as you'd expect. It's 14 volts peak to peak, so its amplitude is 7 volts, the straight sum of 4 volts and 3 volts. But what if I alter the phase of this one? Well, you can see the amplitude decreases. Whichever way I shift the phase. But notice we've still got a sine wave of the sun, and that's the most important property of sine waves. If they're the same frequency, when you add them together, the result is still a sine wave. But what about the amplitude? Well, it's not 7 volts any longer, and with a 90-degree phase shift, it's down to 5 volts, even though the two waves we're adding are still 4 volts and 3 volts. So, obviously, with a phase difference between them, we can't just add the amplitudes of the sine waves to give the sum. We'll be seeing how to deal with that later in the program. But before we get on to that, there's another interesting property of sine waves when they're used with linear circuits. Glyn?
I'm going to start using the simple linear circuit you saw in the last program, a potentiometer circuit or a pot. Remember there we used a DC input and varied the voltage by altering the wiper position. This time the input is a sine wave and this is the circuit diagram. We've drawn the input line right the way across so that you can monitor the sine wave at the top. And the circuit's output comes from the wiper of the pot, and I'll switch it on. It's also a sine wave, and I can vary its amplitude by moving the position of the wiper. There you are. Let's try a square wave this time. Now, if I increase the output's a square wave as well, and its amplitude can be varied by the wiper. So what's so special about sine waves? Well, let's look at a more interesting example. It's this one. Still a linear circuit. It may look complex, but no need to worry about the details. It just consists of 3 types of linear components. It's got variable resistors, capacitors, and these things along the top are inductors. And they're all connected together on the back here. Well, I've changed the frequency to this input frequency to the circuit, so I need to change the time base. And I'll just put the input at the top. Okay, well I can use this circuit and use the probes to look and see what's happening inside the circuit. There and there. To make it a little clearer, let's expand the time base. They're all sine waves, but they vary in phase and amplitude. They have the same frequency, but they all have the same shape. Right, now how about a square wave as the input? Let's just shift that. Now the square wave is the input at the top, but inside the circuit it hasn't kept its shape at all. What about a triangular wave? Again, the input's okay, but inside the circuit, it's distorted. So, that's the important thing about sine waves. They're the only test signals which retain their shape in all linear circuits. When we add sine waves, we get sine waves. And when we put sine waves into a linear circuit, we get sine waves out. But so far, we've been testing each circuit at a single frequency. But as you've seen with your HEK, it's often useful to use sine waves over a whole range of frequencies.
This is your generator scope, and I'd like to spend a few minutes explaining how to use it in case you're having trouble with the frequency response measurements in Unit 2. First of all, switch on. The switch is at the back. And if it's working, you should see a little red light on the front panel light up. Now, the first problem is to find the spot, and I can't see a spot on here at the moment, so first of all, let's turn up the intensity. Okay, still no spot. Move the shift controls. It's probably off the screen. Now, the Y1 shift isn't doing anything, but I haven't got the selector set to Y1, so there we are. Shift it, still no spot. I'll leave it in about the middle and turn the X shift. And there's the spot, so I can bring it to the middle of the screen. Let's focus it up a bit. There we are. And let's see if we can find Y2. That should be okay X-wise, but there we are. There's Y2. So I'll switch back to Y1. So we've got a spot, but now we need a time base. So let's go over to the time base section. We must switch the sweep switch to internal and also the mode switch to auto, and then we should have a time base. There it is. And I'll move it across again to get it centered. Focus it a little bit better. There we are. Okay. Now, the first experiment we asked you to do on frequency response was to check the low-pass circuit. And to do that, I need to put a sine wave into the circuit. So, first of all, I'll connect the earths together of the circuit and the oscilloscope. And then I can connect an output from the generator section across to the circuit's input. So that will give us a sine wave input, but we can't see it at the moment. So if I take another lead and hook it back from the input to the circuit to the oscilloscope input, there's our sine wave. And I'll just adjust the time base so that we have about 3 cycles showing. That's usually the best way to see the sine wave. Okay, that's the input. Now we still can't see an output, so I need another lead which I'll connect to the output of the circuit and take that back into the other input of the oscilloscope. Now we don't see that, of course, until I switch to dual so that both traces appear. And if I move that out of the way, now I think I've got the selector switch set to, there we are, I've got the selector switch set to earth. Now it shows. And if I just make sure the sensitivities are the same, they're both on 1, and both the variable controls should be set to cal. Let's put it. And to make the measurement, you can compare the waveforms like that. The amplitude ratio is about 0.7 in this case, and there's some lagging phase shift. Well, now, we asked you to make a number of measurements at different frequencies, just like this measurement, but there is commercial equipment available which will do this automatically. It sweeps through a range of frequencies and measures amplitude ratio and phase shift for you.
This is typical of the setup used. The key to the process is the swept frequency generator. And this produces a sine wave which gradually increases in frequency. And to see what I mean, just look at the output on the scope as I get it going. Now, to get the frequency response you've just seen, I need to use this as the input to your circuit, your low-pass circuit, and take the output to another important part of the equipment, the analyzer. It's this box underneath. The analyzer is connected to the input of the circuit, and as the frequency is swept, the analyzer compares the input and the output of the circuit, both of them sine waves, and measures the amplitude and the phase change produced. The amplitude ratio and phase shift are plotted on the XY recorder. This direction corresponds to frequency. It's a logarithmic plot, just like the log paper you used. And this line here traces out the amplitude ratio, again logarithmically. The trace below is the phase differences, this time plotted linearly. You should recognize this curve from your own experiment. It's got a break frequency around here of about a kilohertz. Okay, let's run the equipment again, but this time on the amplifier in your home kit. And to do that, I need to reconnect the circuit. I need to take the output of the amplifier to the analyzer and put the test signal into the input of the amplifier. Now, I've arranged for the amplifier to have a gain of about 20, so I need to alter the sensitivity of the equipment, okay? There. And also I've got to re-zero the apparatus and switch on the chart recorder again. Okay, let's go. Well, the amplitude ratio is higher. This is a result of the gain of the amplifier, and stays flatter past the 1 kilohertz break frequency. And first the phase begins to change, and then the amplifier's break frequency occurs. And this is about 5 kilohertz. Well, that's all familiar stuff by now, so let's try something perhaps a little bit more interesting. And to do that, I've got to switch off the chart recorder again. And we're going to connect the output of the amplifier to the input of the low-pass circuit. So let's do that. I'll take this wire, connect the output of the amplifier to the input of the low-pass circuit. And now the two circuits are in cascade. We've got a system rather like this. The filter has a high enough input impedance so as not to affect the amplifier. Okay, what we want to do is find the overall frequency response for the two connected together. Well, let's just complete the wiring. We've got the sweep fed into the amplifier into the filter. We need to look at the output of the filter. Okay, so that's done. But I want to change the paper so that you can see the comparison more clearly. This one's just got the amplifier's response drawn on it. Okay, let's reset. Switch on, and away we go. This time, I hope you can see the phase is beginning to change, and the amplitude ratio much earlier.
Now let's look at those plots in a bit more detail. These are just the same as Glynn's, except that now they're all on the same scale. This first set is just the amplitude ratio plots. Let's consider the response at low frequencies to start with. The low-pass circuit has an amplitude ratio of 1 over this low frequency range. The amplifier has a ratio of 20 over the same range. So we'd expect the overall amplitude ratio to be the product of the two. That is 1 times 20, or 20. And that's just what this overall plot shows us. Now let's look at 1 kilohertz. Now this, of course, is the cutoff frequency of the low-pass circuit, where the amplitude ratio has fallen to 0.7. But the amplifier's ratio is still 20 at this frequency, so the overall ratio should be 0.7 times 20, or 14. Again, the overall plot shows us this. One more check, 5 kilohertz. Here, the low-pass circuit's amplitude ratio is 0.2. 5 kilohertz is the amplifier's cutoff frequency, so its ratio is 0.7 times 20, or 14. So the overall response at this frequency should be 0.2 for the low-pass circuit, times 14 for the amplifier, or 2.8 overall. Okay, so when these two circuits are cascaded, their amplitude ratios multiply together. Now, what about their phase angles? Well, here's a set of phase plots we made previously. Let's look at the same frequencies as before. First, low frequencies. The low-pass circuit has a very small phase shift at low frequencies, and so does the amplifier. So we'd expect little overall phase shift when the two circuits are cascaded, and that's just what the overall phase plot shows us. Now 1 kilohertz. Again, 1 kilohertz is the cutoff frequency of the low-pass circuit, so we'd expect a lag of 45 degrees. And that's just what this plot shows us. The amplifier at this frequency has a phase lag of about 10 degrees. So we'd expect a total lag of 55 degrees when they're cascaded. And that's what we see from the overall plot, about 55 degrees. Let's check at 5 kilohertz again. 5 kilohertz. Now here, the low-pass circuit has a lag of about 80 degrees, and the amplifier has a lag of about 45 degrees, because this is the amplifier's cutoff frequency, 5 kilohertz. So 80 degrees plus 45 degrees is 125 degrees, and this is confirmed again by the measured overall plot. So when these circuits are cascaded, their phase shifts add together. But as I showed you before, their amplitude ratios multiply. Well, that's one way of predicting how two circuits behave in cascade.
But there's another important method using phasor operators. Now this is a phasor diagram, and we can use it to represent sine waves. The length of the phasor represents the amplitude of the sine wave, and this angle represents its relative phase difference, relative to some reference along here. Leading phase differences are by convention plotted as angles in this direction. Here the sine wave leads the reference by about 45 degrees. But similar diagrams can also be used to represent gain, and this is a phasor operator consisting of amplitude ratio and phase shift of a circuit at a particular frequency. Look at the amplifier. The length of the line represents the amplitude ratio, this time at 5 kilohertz, so it's about 14. And this angle represents the phase shift. That is, the output was lagging the input by 45 degrees. Now for the low-pass circuit. At 5 kilohertz again, it had a phase lag, this time of about 80 degrees. And its amplitude ratio was 0.2, represented here by the length of the arrow. Notice that I've had to draw this arrow on a different scale from this one over here, because on the same scale, this one would be pretty small. It's only 0.2 units long, whereas that one is 14. You'll see these drawn to scale in the broadcast notes. So, accepting that the scaling's out, what we have to do to get the overall response of the cascaded system is first to look at the phases. At 5 kilohertz, the low-pass filter had a lag of 80 degrees and the amplifier 45 degrees. So the overall response will be a lag of about 125. And to get the combined amplitude ratio, what we have to do is to multiply that amplitude ratio for the low-pass circuit by the amplitude ratio for the amplifier, and we get a resultant, which is 14 times 0.2, which is 2.8. So I've essentially repeated what David's just done, but in a different form. I could repeat the exercise at lots of other frequencies, and obviously the arrow would change as the gains and phases change. In fact, following the behavior of a phasor operator as the frequency changes forms the basis of a very important technique, and this is used for analyzing the behavior of a circuit over a range of frequencies. Right, that's one way of using phasor diagrams, but remember I said we can use them for representing sine waves. Do you remember the problem that David had at the start of the program? Namely, when you add two out-of-phase sine waves, you can't just add the individual amplitudes arithmetically to give you the resultant amplitude.
The idea of using phasor diagrams to represent sine waves makes that problem easy to tackle. Here's the phasor diagram for the first sine wave. Its phasor is this line representing 4 volts. I take it as a reference, so it has 0 relative phase, and we draw it horizontally. This is the phasor diagram for the second sine wave, with 3 volts amplitude. This one lags by 90 degrees, so it's shown with a relative angle of 90 degrees clockwise from the horizontal reference, so it's pointing down vertically. Now, these two sine wave voltages might exist in a circuit such as this one, which is a resistor in series with a capacitor. The same current flows through both. And the voltage across the resistor, that is VR, is in phase with the current. But the voltage across the capacitor, VC, lags VR by 90 degrees. So that's what these two phasor diagrams show. Now, suppose we want the total voltage across the circuit, VT. This third phasor diagram shows how to predict it. Here, both sine waves are shown on the same diagram. 4 volts across the resistor and 3 volts across the capacitor, lagging by 90 degrees. We get the total voltage VT by completing a parallelogram and drawing in a diagonal like this. VT is called the resultant. This diagonal is the phasor for the total amplitude, and its angle is the relative phase of the sine wave which it represents. You can calculate its length, in this case, from Pythagoras' theorem. It comes to 5 volts. And its phase angle with respect to the resistor voltage can be calculated too. The tangent of the angle phi is 3 divided by 4, and that's about 37 degrees. We show you how to do those calculations in the text of Unit 3. So, if we look back at the sine waves, the amplitude of the sun is 5 volts as predicted by the phasor diagram, and the summed waveform is lagging the top one, that's the reference, by about 37 degrees. So phasor diagrams allow us to predict the outcome of adding two sine waves together, as long as they have the same frequency. But suppose we had sine waves that have different frequencies. What then? Well, here's a sine wave. Here's another at 3 times the frequency. Another at 5 times, 7 times, and 9 times. What do you think will happen if I add them all together?